Good to see you joining in. Should I, we're on 8, maybe I should go ahead and introduce Marcelo. I was just ruminating, a good way to introduce Marcelo, and as anyone who's met me at conferences and things, I always have a different way of introducing people. I met Marcelo at a memorable evening in Falmouth. We were introduced by the well-known Walter Valery, who decided that Marcelo was someone I could work with, and he was absolutely on the money. So that was at least 15 years ago, I should think, Marcelo, a bit more, and really have formed a good
2008.
2008. Oh, there we are. Probably you can remember these things. So I discovered a whole world out there that I hadn't been aware of around the happening in Brazil. Marcelo had been under the great Peter King, gone there to do a PhD, and I really got into the understanding of the mechanics of rock fracture and then bringing that into modeling. And we've greatly appreciated that in the GCC, the strength he's brought into the group around understanding the fracture and then putting the kind of fundamental knowledge of fracture into models rather than just backfitting rates. And that's pretty impressive where he's got to with that. And then a step from there was understanding for the modeling how the energy is distributed in devices and how particles contact. And that brought Marcelo into DEM, discrete element modeling. So he's put a lot of effort there because that creates the link between the particle and the equipment. And we're highly aligned on this. He's just way ahead of me, of course. So really looking forward to Marcelo revealing what he's learned in that process. It's a long and rocky road, if you don't mind the pun. So over to you, Marcelo.
Well, thanks a lot, Malcolm, for the kind introduction. Indeed, 2008, I met Aubrey and Malcolm just at once. And I didn't meet Hakan at that time because I think for some reason he got stranded in Turkey and couldn't join us in Falmouth. So quite a memorable conference there. So I'll start joining. Thanks, Malcolm, for that. And so I'll start joining my screen. I think, let me check if it's operational. I don't know. Okay, I assume you are seeing. No, let's just see the full screen now, correct? Okay, excellent. So hello everyone. So it's definitely a pleasure to be here. And indeed, I think since it's the first time I present something in these GCC seminars, I wanted to try to a little bit during this next, I don't know, 35, 40 minutes, talk to you about a little bit of the path. We went through this, I don't know, 20 some years that actually put us on the look at comminution and degradation using the same vision, which is actually to put DEM and breakage together. So the outline here of my talk is after a brief introduction, I'll talk about the modeling of breakage that we have been pursuing, and then of course go to the thick of the presentation and looking at different approaches and how we think breakage can be best coupled to DEM. I think in this crowd here, there's definitely very little doubt that people recognize that DEM did a fantastic work for us in process industries. I'd say it definitely allowed us to open the black box. So before we couldn't look inside the machine, now we can look at least in the virtual machine, what's going on there. And I think DEM for these last 30 years has evolved to a level that you can choose whatever platform you want to use, open source or commercial packages. There's plenty out there, as well as some in-house codes. And indeed, when you look at some things such as chute design during materials handling, or maybe closer to home here, new liner design, considering projection of charge, there is little doubt that DEM is already an engineering tool. A lot of those are designed every day throughout the world and checked using DEM just to make sure things are already functional. So we want to go to this level in comminution and degradation during handling, but it's still something that is work in progress, I'd say. We still are working towards this direction, and the challenge I believe, is obviously because of the difficulty of describing breakage in the environment, as we will discuss during this presentation. Then, so my provocation here is that in order to do this, we have to look very carefully what is the best way to couple these technologies together, these tools. So breakage modeling, as Malcolm introduced, is, in my opinion, quite in the heart of the success of this venture. So there's no shortage of breakage models or breakage equations in the literature. Over 100 years of research on that. Our vision is that the only way that is sustainable to really couple breakage to DEM is to look at individuals, understand what happens at each individual particle. So it is really the best way to use DEM, because indeed the best thing we can do with DEM is actually describe not averages but individuals, and that's really applying to the environment, to the machine, to the device, but also to applying to the particles. So there's little sense in actually using a richness of information from DEM if you're actually just relying on average characteristics of particles and tracking just averages of the population. The nice thing here is to be able to have as much information about both. So, but in order to do a good job coupling DEM and breakage models, I think some requirements are important, in my opinion, is that the models should be detailed enough to describe breakage, but they shouldn't be overly complex. We should always remember that there's little success in being able to describe fantastically well a single particle if you cannot really put hundreds and thousands, even millions of particles in your simulation. So you have to avoid much complexity or computing effort. Also, it's important that your models have to be detailed, but really they should be amenable to be fitted from bench scale tests, hopefully relatively simple tests. But as important as those is that we want to be able to provide physically sound descriptions over wide ranges of conditions that we find in practice. For instance, we shouldn't be able to just describe well a couple of sizes. Every time we handle in break particles, we generate potentially very fine material, even with small amounts. So our models have to be able to at least give reasonable descriptions over wide ranges of sizes, stressing energies, because of course in the end you can have the lowest until saturation stressing energies. Particle history here is important, being able to keep track of what's going on with the particle, and also the fact that sometimes particles hit each other, sometimes they hit different surfaces, and that surface, of course, as far as comminution is concerned, will have a major load. So these are all things I think are key in being able to successfully model breakage. Indeed, over 25 years ago, I started with University of Utah there, and as part of my PhD, some really good work was being done there. I pretty much hijacked some of that to Rio when I started 23 years ago in Rio. And the idea is that I started building the blocks of each of the components I thought were important to be able to describe breakage from individual particles to an environment. I call these submodels, and of course we have been busy publishing and validating each of these using data from testing. So I'll go through each of these just in a little bit more detail here in the next slide. So basically the first and I guess a key part of the approach is to describe breakage probability. So we know there's a number of different functions that look like this S shape here. When you look at the stressing energy here on the x-axis and the proportion broken on the y, we know variable gamma function. We use the log normal distribution with an upper truncation just because it really gives very explicitly the median value as one parameter and the standard deviation here. But basically this has served as well, and it pretty much like these data here for iron ore pellets, breakage probability values, describe fairly well the variability for most materials we have seen so far. So this is one that accounts for the variability in the material response. We know that even particles of exactly the same size and same composition do not really behave exactly the same. And this really accounts for that. The second part of the story is if you look at the breakage, the median value, that is the 50% probability value here, the specific energy required to do that, which is the fracture energy or median fracture energy. If you look at this value, how it changes with particle size, it changes in a very particular way for each material. Sometimes it can go to, for very coarse particles, to nearly constant values here, and then increase quite dramatically for fines. Sometimes it's just a single slope, regardless of particle size. So these, we use this equation based on reliability theory that has essentially 3 fitting parameters here. But on top of that, it also accounts for the stiffness of the surfaces. So it really is sensitive to the fact that sometimes you have softer surfaces that absorb some of the energy, whereas in some other cases you have some very tough surfaces, or basically very stiff surfaces that really give almost all the energy to the particle. So this is the other key part of the model, which means that we want to understand how the particle strength changes with size. The third part of this model approach accounts for the fact that when particles are hit with an energy that is insufficient to break them, their energy is reduced. And it's reduced by this damage amount that the particles sustain. So based on continued damage theory, we put together this model here that tells us how the amount of damage varies as a function of the fracture energy of the particle here in the denominator, and in the numerator, the stressing energy. So you basically fitting this single model parameter gamma here can be done by, for instance, hitting particles, a bunch of particles over and over again until all of them fail. So with the proportion broken increasing here, you can actually describe how amenable a material is to that repeated stressing event. So this is a nice, elegant, simple model that really describes fairly well data for a range of materials. The fourth part is the one that is quite familiar to us, is, let's say, the single particle breakage function, the body breakage function, which is described using those T10-like equations, quite familiar one here, with the key difference that in the denominator, there is the median fracture energy that showed in the previous slide. So it's actually normalized in respect not only to particle size, the T10 method, but also in respect to the strength of the particles. So by doing that, we can actually superimpose data for different sizes, as you can see here in the picture, the T10 for different sizes as a function of stressing energy. And on top of that, we create the full size distribution from each event using incomplete beta function, which also served us well. The very last piece of the puzzle here to be able to describe in every single event what's going on with a particle is this surface breakage mass loss or attrition loss. And it's described using this simple expression, which is the amount of material lost is a function of a material parameter, particle size, and the specific impact energy. So this model is essentially Gadiri and Zhang's model from several years back, applied to the data, the range of conditions we find here. So it is, you can see here just a comparison of some experimental data points for different stressing energies and the amount of mass loss you can find for different materials. You can see here some different rocks, iron pellets, and so on. So it's still, this model is, of course, it's a very tough area to deal with, surface breakage, attrition, chipping, and we know it's very dependent on particle shape and so on. So I'd say that amongst all the models, this is the one that is the latest and the most immature of the models, but at least it really contributes to explaining what's going on with particles under very low stressing conditions. How do we go by defining constants in those equations and fitting parameters in those single particle models? So the most favored approach is to look at single particle breakage tests. You can see here the impact load cell device that was originally proposed in the University of Utah. There's a number of them around the world, here in Rio, of course, at the JK, in Iran and other places. Of course, this is nice when you want to reproduce conditions that you find in most Comminution machines, low, relatively medium velocities. If you're looking at machines that apply loads very slowly, it's a good way to go by compressing. So slow compression tests are quite available everywhere around the globe from different presses. But if you're talking about very fine particles, there are even the opportunities, some fancy slow compression systems like these that we have that can allow us to break particles as fine as 30, 40 microns one by one and measure the energy required to break. And of course, if you're dealing with some conditions, for instance, like in impact crushing, or if you want to mimic what happens during ship loading or materials handling, you can go to one of many impact testing systems there through which you propel particles against a target with different angles and so on, and then analyze the debris, count the number of broken particles and so on. In materials handling, some materials are quite brittle, so you can even do simple drop by gravity tests and analyze the results. So there's a number of direct ways that you can go by measuring those parameters. But of course, in some conditions, we have to rely on indirect measurements. For instance, Grant and Malcolm did some very nice work a few years back on using Erlang's Schonet's impact device here, as well as JKRBT, to generate data to describe over quite a range of particle sizes, how a particle varies their response. Using data that they generated and using our modeling approach, we could demonstrate that we could fit data very nicely here over quite a range of different sizes. The key part of our model, which is exactly how the medium fracture energy changes with particle size. Another indirect, more indirect approach, I'd say, is to use, for instance, batch grinding tests we do in the lab, either, I don't know, like a ball mill or a stirred mill, and then rely on the validity of the model that I'll just show in a few minutes on batch grinding mechanistic model. We can back calculate some of the material characteristics. In this case, this is the limestone data. So we have been publishing on this, demonstrating that, of course, within the limitations, it is a valid approach, but just in a way to be able to still get some meaningful model breakage parameters to be using in the different approaches you see downstream. But it's important to bear in mind that the model has limitations. And some of the limitations are referring to, for instance, strain rate effects. We know that some materials exhibit strain rate effects, and it's something that still we don't quite fully understand the relationship between material composition and texture and strain rate effects. So that's not really explicitly in the model. What we suggest is for you to do testing in the conditions that you are closer to your device and the strain rate range. The other thing is about particle shape. We know particle shape, of course, has a very significant effect on breakage. So far, we assume that particles that are tested on the same shape range that you see in practice. But of course, this really imposes a challenge in particle preparation during testing. And that's an area that I think can benefit from further research in the future on breakage modeling. Loading mode also, we know is for some materials, if you're stressed by hitting against the target or load, like in 2 points compressing, there are differences. These are not quite clear in the literature. So our model is insensitive to that. That's another area. And also composite particles. We assume particles have their variability, but we don't really know exactly which component inside the particle is responsible for the strength and so on. So behavior of composite particles is something that we don't really yet understand, but it's really an area that is key in liberation. So bearing those in mind, we still thought that now we have a model that is good enough to be doing some good work for us in degradation during handling comminution. So we want to deploy this breakage model in simulation. How do we do that? I think to illustrate that, I'd like to just show this table with, in my opinion, at least 4 different approaches we can go by doing that. We go through it in the next few minutes. The first one is to break particles in DEM using collision history information. In this case, this approach is the simplest approach. You consider the discrete particles. In this case, we track the individual particles and predict what happens to each individual particle. In this case, it's basically a post-processing of information from DEM that we use to get the collision history. and then afterwards we predict what happens with the breakage. The other approach, the following one, also looking at discrete particles, is one, the most intuitive one, is the breakage embedded in DM. So DM in this case is encompassing what is going on throughout the whole process. In this case, DM is used to calculate the stressing energies, describe each collision, but also as soon as a particle breaks, it replaces by fragments and so on. This is the one that we'll talk about also quite a bit. The third approach now goes into a continued distribution. Now it recognizes that for some media meals, for instance, there's no use to try to describe each individual particle. You have billions and billions of particles. In this case, we want to use what we call one-way DM-PDM coupling population balance model, which is basically running DM simulations and then getting information on the collision spectra, typically of media meals, and using some particular form of population balance to predict the outcome of the process. So the very last one, which is pretty much just a step forward the previous one, is what we call the two-way DM-PDM coupling. In this case, we run the DM simulation, and then we run the population balance model, but then we recognize that the DM simulation may be changing because of the outcome of the breakage. So we go back and iterate with the DM simulation and so on until you reach convergence. So these four approaches you'll see are not necessarily applied to every single case, but we understand that by careful examination, we can identify what is the best fit for purpose solution. So looking at the very first one is the breakage from collision history. I think it's a very good option when you have very limited breakage in your process. So just explaining very briefly, this would mean you run your DM simulation, assuming that particles don't break. It's the easiest way to go. That's pretty much the standard outcome of a DM simulation. But then you keep track of several particles looking at their collision history. Now with this information, after simulation is finished, you can go to your own code and start to look at these histories of these virtual particles and understand what would happen as far as breakage if these particles would be simulated. So in this case, for instance, the first outcome is that what if the stressing energy in one of those collisions is lower than the fracture energy of the particle? We know from our breakage models that the particle probably suffered surface breakage and may have been damaged. So there's a mass loss here, fragments generated, also a reduction in fracture energy for this next time step or next event. Well, now you go to the next impact event on this same particle. Maybe the stressing energy is higher than the actual fracture energy of the particle. In this case, the model allows you to predict the body breakage and then the size distribution of the fragments and so on. So it is, of course, a limited approach when you have a lot of breakage because the simulation doesn't consider that particles would be broken. But it's really a very powerful scheme when you have fairly limited breakage. So to illustrate this, just pushing almost to the limit of the validity of this approach, we applied to a VSI crusher in a particular application here in Brazil, producing artificial sand from crushed rock. So this is one VSI crusher. So what we did, following exactly that approach, is run DM simulations, and then running simulation, we got information on the collision history. You can see here, just for 4 particles over a few seconds, quite a few collisions, minor collisions, major collisions, but a lot of very low energy collisions happen. So we wanted to be able to now, using this information, feed to the breakage model, considering the whole history. What you can see here, the typical particle size distribution, here the feed and the size distribution of the product, discharge of a full industrial crusher. You can see here the effect of increasing the rotor frequency from 1,000 to 1,400 RPM. And you can see the data points as well as the model quite reasonable in the sense of increasing fineness as you increase the vigor of the impact. And also showing here the typical thing we see in VSI, that a lot of particles actually barely break. This size reduction is certainly the smallest amongst all comminution equipment. So it actually is, of course, just in the limit of applicability of this approach, but still served us well in a simulation involving millions of particles, as you saw. So this is one approach that could be considered. Indeed, as a limitation, it really provides unrealistic description if particles suffer multiple breakage or severe body breakage events. So, and the other thing is, of course, it's not packaged anywhere. So you really have to build your own code or look for somebody to do that for you. But it's important that we have been very successful simulating a number of materials handling operations using this tool, because you can consider, for instance, when you do materials handling, especially loading in a silo or things like that, or loading in a blast furnace within this picture, you can have millions and millions of particles. And it'd be a lot of effort to actually predict breakage in real time with DEM here. It would put a lot of overhead in your simulation. So one thing you could do is just run the simulation as you would without breakage, and then looking at a few tracked particles to see what happens there. And this has been very useful for materials handling and a number of applications. Well, of course, the most intuitive approach we would consider when you're talking about coupling breakage in DEM is actually putting particles breaking in real time inside the DEM environment. And indeed, I think that's the only option you should consider if you are, for instance, considering predicting a crusher with flow restrictions, like a compression crusher, jaw crusher, or cone crusher. In that case, there are a couple of options you should consider. We are quite familiar with some of them. For instance, we can actually deploy this breakage with at least two major types of approaches. The first one is in which the fragments are resolved throughout the whole simulation. So I call this the fully resolved fragment approach. As you can see here, the scheme on the right. For instance, for the bonded particle model, here you can see particles, the fragments exist from the first moment you start simulation. So it is, you can appreciate that the amount of energy, the amount of time and effort in the computer there is quite significant, because you have to keep track of every individual, even before they are actually created in the simulation as far as fragments. And then there's what we call particle replacement, is that is schematically here on the right. You only care about the fragments when they are actually created. And this is exactly the approach that we favor, because it's more amenable to be deployed with large simulations. So this instantaneous breakage approach, as I mentioned, it's one that fragments only appear when you need them. And the particle is replaced by the fragments only when a given criterion is met. As I mentioned, it's far less computationally intensive than the other alternatives. That's why we pursue that path. So what did we do? So we were quite happy with the approaches we put together. And then we're very happy to be approached by the two major software developers here for commercial DEM, Rocky, ESSS, and DEM Solutions, now out there EDEM, that they wanted to have our model input in their platform. So the difference here, more than a year ago, we inputted in Rocky the version for polyhedral particles, and here in EDEM, we just recently inputted the version for spherical particles. So the two are working there already if you have licenses of either one of them. So the first thing we needed to do is to make sure that the models were correctly represented inside the DEM codes. So going from the very first verification is to compare the model equations, which are given by the lines here, to the simulation. Simulations here is that we do exactly as we would in the lab. Hit many particles with given energies and record the number of particles broken, either in a drop weight tester or in a single impact system, and also looking at different particles, for instance, for a copper ore. What you can see here in this picture is very nicely, we represent exactly what is going on with the populations, that at very low stressing energies, very few particles suffer body breakage, and at very high stressing energies, you break everything. The simulation is there pretty close to what we know from the model. You can see here the illustration. That is in EDEM for spherical particles, and on the right here, you see exactly the same thing for polyhedra. So sometimes a small effect here from single to double impact appears, but that's not really accounted for in the model. The second part of the puzzle here refers to the weakening, which is basically accounting for the fact that particles, when they're hit over and over again, they become progressively weaker. So they, even at the same stressing energy, they eventually do break at a very low impact energy. So this is characterized by a single model parameter here, gamma. And you can see here both in EDEM and Rocky that it really captures nicely the progression of particle breakage. And here on the bottom, you can see a simulation in Rocky showing the progressive breakage of particles, so on and so on, when they're hit, they are led to drop. Perhaps the most challenging part of the model when you embed the breakage model in BEM is to be able to predict the size distribution. And anyone who has done that with bonded particles and so on knows that quite well. You can see here on the right, for instance, when you look at Rocky, looking at propelling particles against a target here with different stressing energies. Here the model is given now by the symbols, and the lines represent the simulation. You can see here that it accounts very nicely to the fact that as you increase the stressing energy, particles become finer. In the case of Rocky, we still have the limitation of really only describing the particles that are explicit in the simulation, as you can see here, but very lifelike breakage you get using these polyhedral particles. On the other hand, more recently in EDEM, we are using spheres, so it does look a little bit funny like these, particles being superimposed and then generated. But on the other hand, you can see here that we could represent very nicely what happens in practice. Here the lines represent the model, and the symbols, the simulations. You can see that it captures very nicely the increase in particle fineness as you increase the impact energy. But more interesting, I guess, is to show that the minimum size of particle is given by this dotted red line, which is about 1.5 millimeters. And still we could use a method here to extend the size distribution to these sub-DEM particles, because we know how particles break from our models. So this gives us a lot of confidence that we can do a good job starting to apply to the real situations in comminution. Perhaps the simplest situation we can find in comminution is just dropping a particle on a bed, a steel ball on a bed, on a monolayer bed here, copper ores. You can see here, this on the left is just a comparison now. Symbols represent the experimental data and the lines the simulation. So it shows very nicely that increasing the impact energy of this ball, which typically is raising to a higher height, you increase the fineness. So qualitatively and quantitatively, giving a very nice fit here for EDEM and also for Rocky. They also pay attention to the fact that in EDEM, we could stand quite a lot below the minimum size of the fragment, which is in this case about 0.8 millimeters. So give us some good high expectations when we apply to larger scale systems. So just a couple of examples here. Very recently, we have been running some of these simulations. This is a Siemens type cone crusher we have in our lab. So we have tested quite a few materials. So we ran the simulations, for instance, for a copper ore here in the 22 to 16 millimeter size. And we ran simulations now in EDEM using spheres, and in Rocky using polyhedra. The speed of simulation is quite different here, almost real time in Rocky, but quite slow down in EDEM. But nevertheless, you can see very nicely the choke level being identified here, and then the fines leaving the machine. It looks quite lifelike what we have. But we're interested in seeing some quantitative information, and you see here, the red line, the horizontal red line, is the experimental throughput, and the actual measured throughput you can see here. Quite close, so we're confident that it's capturing the actual flow of the material, which is related to the size distribution of the fragments. But more exciting even that in EDEM is the fact that we can actually predict the size distribution even well below, you can see here, the minimum size of particle that appears in the simulation, which you see here in the solid line, red line. in contrast to the size distribution measure from the test. So these give us confidence that in crushing, we can apply to some really interesting case studies. We have done these some industrial ones, but we didn't get clearance to present today. So maybe the most challenging crusher type machine would be the HPGR. Quite a few of us are involved in that. So the HPGR has the added complexity that you have one row that is fixed, whereas the other one is movable and responds to the stresses in the bed. So in this case, we needed to do DEM and MBD coupling, multi-body dynamics, and we did this recently in Eden. So you can see just an illustration here for crushing an iron ore, just narrow feed size. That is not really suggested to do that, but since we had some data from a small lab machine, you can see here how the throughput changes with time, so about 2 tons an hour, a little bit overestimated throughput, but still quite reasonable for a given applied force. And here in the bottom is the gap. So the gap is not fixed. We respect what happens in practice in the simulation. We start with a 0 gap here of 2 millimeters, and then it moves up and down until it reaches some given level. So it's still very short simulation, just done a few days ago, just for you to appreciate that even this machine is amenable to be simulated. But when you look at size distribution, I think it's quite exciting to see that for instance, when we raise the force from 33 kilonewtons to 143 in this small lab machine, we see an increase in fineness of the product. As typically as you see in HPGR, a lot of fines. But the nice thing here is that you can we could capture the increase in fineness in the simulation given by the lines. So very excited to see the simulation is telling us what we do see in an experiment we do in the lab. So, of course, there are still limitations to that. We're still in the early stages. For instance, particle shape, we know that influences breakage. Even though we could actually tailor-made, for instance, in rocky, the shape of a particle, we have no control over shape of fragments. So this is still an area that has to be addressed in the future. And of course, when we deal with spheres, there's no control whatsoever in that. It's important to recognize that when you have a lot of rebreakage, major rebreakage going on, simulations obviously will require inputting very fine particles there. So the tricks that we use to generate the fines no longer become applicable because those fines would have been broken over and over again. One area for those who are very excited about DM that is really worth looking at is that when you talk about contact parameters, we mostly look at how unbreakable particles behave. And in comminution systems, particles change their size naturally. And so their flow properties will change. So we have to be a bit more careful than usual on selecting proper contact parameters in that. So of course, this hasn't limited us to apply to comminution machines. We have been doing work in impact crushers, jaw crushers, roll crushers, and so on and so on. And of course, the most exciting thing I'd say in this case is actually go to novel crushing devices and being able to test this machine to things that are not even in operation yet. Well, so this is the first part when dealing with explicit particles, individual particles in a DEM simulation. But how do we do about simulating tumbling mills? Tumbling mills, you're talking about huge particle populations there. And just to illustrate how massive that is in a DEM simulation, for instance here, I'm just putting for this different mill types, mill diameters, starting from a 30 centimeter diameter mill, like a bond mill, the number of particles you would have just to simulate the full mill, 30 centimeter long mill here. Now you have maybe a couple of hundred particles there, pretty straightforward. But then as you increase the mill size going to the full industrial, if you're only simulating media, you're talking already about a couple of 100,000 particles, which is quite doable these days, no question about that in any open source and DEM code. But now if you want to start including particles, just in the case of the bond test, besides the media, just the 2.8 millimeter particles, which is not a lot in a bond test, you already increase 2 orders of magnitude the number of particles you have to deal with. If you're even greedier than that, including 0.5 millimeter particles and so on, you're definitely going to the billions and trillions of particles, which is never, not going to be available for quite a while, I believe, for us to simulate. And this is only talking about particles that don't break. If you talk about breakage of these particles, it completely goes out of control. So it really means that we need to, as much as possible, remain looking at how media behaves, because it's still doable, and be smart about coupling with breakage. So in this case, we have to really understand that in order to apply this, we have to consider that only grinding media is transferring energy. But it's important to also realize that we should assume that particles don't really create a lot of swelling in the ball charge. That applies if the ball, the particle size distribution is not too coarse. It's important to also realize that the contact parameter selection is key here. We must be able to mimic with the contact parameters the presence of slurry or ore. And that really is different from the contact, for instance, for steel on steel. And one of the resources we have to make sure that we are in the realm of reality, we should be able to match the actual power in the machine with the power that we simulate in the EM, summing up the energy loss. So with those caution notes, we have applied the scheme, which is slightly different from what you see before. Now it's in a continuum. We use DEM simulation to get the collision energy spectrum. Now we have the data over quite a range of stressing energies. We have the same models we saw before, giving a description of the micro scale events, but then it requires us to understand what happens between those grinding media collisions. How much material is being captured? What is the size distribution of those particles? To be able to finally put in this population balance approach and what we call the fracture energy convolution, which accounts for the fact that when you hit particles, some of the weaker particles are being broken, some of the tougher particles are going to be weaker. So we have to mathematically account for all of those events. Just for you to appreciate how this population balance formulation looks like, if it's batch grinding, it looks more or less like this. Is the rate of change of particles in each class is a function of the frequency of the collisions from DEM, the mass of particles inside the mill, but also of disappearance and appearance components here, accounting for both body breakage and surface breakage. Just for you to appreciate the level of complexity of what I'm talking about, we have to account in each of these terms for all of those micro processes, the amount of material captured, the frequency of collisions you have of a given magnitude, and the probability distribution or the fracture energy distribution material. So it's a lot of background modeling that goes in there to be able for us to really put these together in a continuum. One part of the model that I think is quite important is this mass capture. So you can see here that the amount of material captured in our model is a function of the diameter of the ball, the particle size, which gives us something that we know that if you increase the ball size, you capture more material, but of course you have fewer balls for the same grinding charge. So these are all the pieces of the puzzle that we put together. And then of course we have done some years ago validation on these, on different grinding conditions in batch mode, from fairly fine copper ore to relatively coarse rock. Fairly good agreement here. Some cases it's not as good because we have difficulty in getting good breakage parameters for the fines and so on. But then I think one way to show the validity of this approach is to show that it responds sensibly to variables that we know are important in milling. For instance, the surface breakage rate here, we know that if you use large balls, like 40 millimeter balls in a small mill, the rates of breakage are quite low for the fine particles, but you get the bonus of breaking the coarse material. If you decide to move to very fine particle balls like this, 15 millimeter balls, you definitely sacrifice the breakage of the coarse in favor of being able to break fines much more efficiently. This is a very nice material dependent response we have here that the model is already capturing very nicely. And also now going to other mill types like a stirred mill, vertimill type machine, we know very well that increasing the frequency of collisions, you increase the energy, But here in the model, you can see very nicely that the specific breakage rates pretty much shift upwards as you do that from prediction using a model. So it is something we're very excited about, the ability to represent what we have seen through experiments using the mechanistic model. So how, of course, in industry, we don't operate things batch, they are continuous. If you want to go through the full dynamic solution, it gets quite complex. It's major integral differential equations. But we wanted to at least have a simpler solution. And for instance, not looking at the dynamics, but at the steady state, we could use a simpler solution like this using batch grinding data as well as residence time distribution. So using this solution, we could actually go into a commercial simulation platform, which is a dream of us for a long time, to be able to put a DEM-based breakage model into a simulator. And this we have done in IES. You can see here our ball mill model with the classifier, and then predicting you can use in IES in any circuit you like. So to illustrate this, we simulated a ball mill producing pilot iron ore pellet feed. Went through the whole steps of scanning the industrial mill, running the DM simulation, getting survey data, and then comparing what the model predictions gave compared to the experiments. See, here on the left, we looked at the case as if the mill was open circuit. So looking at the combined feed versus the product, you can see here the model could nicely capture the size distribution of the discharge. But more interesting here on the right is the case where you have closed circuit operation with the full cyclone and the discharge combined. So you can see here the full fresh feed, and then the discharge, and then the overflow, and under an overflow cycle. Here on the bottom, you see that, of course, in this case, it requires iterating between the mill model and the cyclone model, and that pretty much over in 30 iterations, it reached stability. Of course, that even in a commercial software like that, it took, I don't know, maybe 30, 40 minutes to do the simulation. It takes a while, yes, to solve all those equations, but it converges and it gives us the full circuit response. So of course, there are still limitations on that, indeed. We still know relatively little of the role of slurry, especially on breakage and particle capture. So we still need to improve, especially on the capture model. And of course, characterization at fine sizes is a key challenge that we need to address to be able to apply these approaches. But that hasn't prevented us to look at different mill types, stirred mills, planetary, and so on and so on. So the very final piece of the presentation here is talking about this 2A DM-PBM coupling, because we do acknowledge that in some mills, for instance, ag and sag mills, the particles take an active role in energy transfer. So we cannot really simply decouple the role of media and ore anymore. So in this case, we could say that let's look for that approach where you break particles inside DM. We don't think that's an option for sag mills simply because it takes fairly long for the charge to stabilize. You're talking about a simulation that would have to take several minutes, and we still are running DM simulations for seconds, not minutes, not hours at all. So in order to do that, we need to come up with a new approach to couple DM and population balance to do this in a smart way. That was the PhD of Rodrigo here from my group. The idea is essentially to start with the initial charge, doing a DM simulation. After that, getting the collision energy spectrum, exactly as we do in ball mills, but then feed to a breakage model to be able to predict if the charge has changed or not, or only fines have been generated. If not much change has happened in the charge, you can just iterate the mechanistic mill model here, assuming validity of the DM simulation. On the other hand, as soon as the charge changes enough, you have to go back and redo a DM simulation, and then you go to the outside loop. We have done that for a couple of cases, but an important thing here for sure is to recognize that in a sag or ag mill, you have the discharge grade that imposes a classifying effect. In this case, we have to use an assumed discharge function. We don't predict that. it's from experiments or simulations using SPH that we need them, but we needed to assume that discharge function to be able to do the simulation. So we went to a pilot mill here for copper ore. You can see the simulation here. But just to illustrate one point is that the amount of fines we generate here from the simulation, it goes through the dynamics of the population balance, but then requires updating the DEM. So every time it changes dramatically, the slope here is because we did a new DEM simulation to update. So maybe after a few minutes, we could get full convergence, as you can see here. And the full convergence solutions are illustrated in this graph for the mill, the same conditions operating in SAG mode on the left and on AG mode on the right. You can very nicely see that the model could fit the data, predict the data. There's no fitting. And even further, showing that AG milling produced a bit more fines than SAG milling, as we already know from practice. So it's still, indeed, there's still a long way to go on this coupling approach. It's still quite computation intensive. You require a discharge function, and it's not yet packaged. But there's definitely great opportunity to apply to pebble mills, run-of-mine mills, and so on. So this really puts me into the final slide here. I think the take-home message I'd like you to take is, I think there's no one-size-fits-all solution to simulate comminution in degradation DM. You have to look for the best one. And I think it's always good to remember that we're not in the animation business, and we should really seek the best fit for purpose solution, not the one that looks good, but one that works well. I think breakage modeling, I believe it has a central role in that. Our breakage model now is available in the major soft commercial DM platforms. We're very happy with that. I think also we have been able to put our breakage model and the population balance model in IES to make room for more people to test the approach. And as I said, that I think AG and SAG mill still is a challenge, but I think that's probably one of the devices that can benefit the most from using this simulation, because the models, the phenological models, are definitely challenged if you have few little data. And I think also the final conclusion that I think viable approaches are already available for most simple problems involving degradation during the handling and comminution, but there's still work to be done in order to really make them truly an engineering tool. So I'd like to thank obviously my whole team for all the background work, fantastic work done over the several years here. I won't name each of them. And of course the software developers, ESSS and Altair Eden, for implementing the breakage explicit, and of course the industry sponsors. Well, thank you, and sorry to take a lot of the time.
Shall we give Marcelo a round of applause, please? Thank you very much. I think we can take questions so that we can have a bit of a discussion after that stirring presentation. Let me just call up participants. You can either raise your hand with the software, or you can just switch on your video and raise your hand, whichever is suitable for you. Okay. Questions for Marcelo?
May I start, Aubrey? Yeah,
yes, Mojtaba.
Yeah, Marcelo, great talk and indeed great progress. Congratulations. I'm really very impressive range of work you've done. Two thoughts in my head. One is, what is left for us to do?
Wow. Well, I think as I said, I putting some provocations there. I think it's there's a lot of the coupling tools, for instance, that you guys have been doing with CFD, and also multi-body dynamics and things like that. I definitely some of the key things in some machines we don't even get through the door without going that. You showed in your very in your great seminar there the case of the airjet mill. But I really do think that we need to start using these and understanding the flaws and where we should really focus our attention on the breakage side. So I'd say that there's definitely plenty. I'm try to pave the way a little bit, at least putting some, I don't know, on the breakage modeling side, trying to define what is the least information you need to have to start doing things that make sense. But there's definitely a lot to move forward to. Thanks,
great. So in terms of limitations for the embedded DEM, you mentioned it was a mid-slide about the limitations on shape and when we have extensive breakage, and there are limitations. But at the same time, Marcelo, you had very good comparison on your simulation with experiments. So I think what I conclude from that is that the judicial choice of parameters is paramount in a way. How do you?
No, absolutely. So in this case, indeed, I think having the proper parameters in that was critical. But keep in mind that, of course, the very good agreement we got in the verification stage, where it's just a single blow to a particle, and also the crusher that I showed there in the HPGR in these particular situations represented situation in which particle was broken maybe just a few times. So the parent particle was broken and the debris was broken just one or twice. If you have really a situation where massive rebreakage happens, that's when things really get far from reality. But absolutely, you're right. I think being able to fit the proper material parameters there is critical to be able to do a good job in predicting breakage. So what I'm trying to show is that there are things that we can already do probably well, and other things that are still further down the line. You're even talking about today's computer resources.
Thank you.
Thank you, Mujtaba and Marcelo. Any other questions?
Of course, I have some. It's hanging back.
Thank you,
everyone else put their hand up. It's an interesting aspect. You just touched on it there, Marcelo, was the breakage testing. So when we come to, right, I want to simulate my mill, and I have a drop weight test and a bond test. That's not what you need. Part of what you did was some backfitting, but we don't have a generic availability of these more advanced breakage tests. How do you think we go about that to get them into mechanistic modeling?
Yes, no, I think that's a very good point. Unfortunately, I didn't have much time in this presentation to pursue that. But I think the provocation was along these lines that, yes, I think in the worst case scenario, we can use some of the results that you might have on a bond work index test, drop weight test, to assume some of the parameters and backfit some others. But definitely the sustainable way forward is for us to really put together some tests that we can run fairly consistently and rapidly in the lab to be able to generate the proper data. I think Arno has a nice test right now that it's a rigidly mounted row crusher that is quite nice. And I think there are some nice impact tests, for instance, from the area of materials handling and from attrition that we can actually use in that area. So I think it is something that we have to, as we put out there for industry to start to use, we need to really put together tests and protocols on how to determine these parameters the best way, but still be able to describe real processes. But we are moving in that direction. I think there's great opportunity indeed in that area. And I think at GCC, we have to really collaborate as much as possible with our partners to really put out there the new generation of breakage tests.
I think a GCC mission.
Indeed, absolutely.
Any other questions from the floor?
Yeah,
Tony.
Yeah, a comment rather than a question. Marcelo, thank you. That was very refreshing. And just the one comment is sort of already been alluded to, that because you were always checking with the applicability in mind, you are actually quite advanced in other words, you are not too far away from, as soon as you find something, it could almost be applicable because you judiciously chose your parameters. And I really like that kind of approach. So you're not skimming up on the research, but you're never too far away from applicability. And I want to commend you for that. Very nice presentation. Thank you.
Thank you.
Yes, I think the idea is exactly that, is to not really look at the pie in the sky type of thing. It's really make sure that we do things without fancy computers. Those are computers you can buy here and run for maybe a few days, but really be able to deploy to industry machines. Please, Grant, I guess Grant is looking forward to it.
I was just scratching my head. I had a question. Just you showed a fantastic presentation. It's always wonderful to listen to you and understand more. And it was great to see that you'd been able to take some of those testing results that we put together. I haven't seen that paper, so I'll have to read it now. So I'm looking forward to that. You showed that you used Rocky and EDEM for that crusher results, and you showed just the EDEM results out of that. I mean, you might not be able to share it, but were the parameters the same in Rocky and EDEM in terms of the material properties, and did you get similar results out of both software? I mean, that's kind of useful for us to know.
No, absolutely. Yes, absolutely. So actually the results from Rocky are the ones that are actually published. So you see there, it was already published early this year in Power Technology, so you find. But it's a very good point to raise that, yes, the parameters were exactly the same for those two cases. I think the tricky part, and I think I kind of alluded to that, is that if you're talking about a cone crusher, it is a device that particle shape is a key. So, of course, if you deal with spherical particles, the crusher will look at those particles with their real size. Rocky, on the other hand, it creates flaky particles. They end up escaping the crusher quite readily, more so than real particles. So the size distributions changed quite a bit. I didn't end up including that, but it actually created a bias towards EDEM, creating a final size distribution, whereas Rocky created a coarse. And that's basically because of the fragment shapes. Except for that, everything else was exactly the same. The contact parameters, breakage parameters, no fitting to each case. Of course, if you want to fit exactly the match power, the match throughput, you had to do some fiddling. We didn't want to do that, just to be able to show that we are in the realm of reality in both
Thank you. I'll take a few questions. I'm mindful of the time that we are running late, but we want to have a bit of discussion. We may stop at 1:10 so that we can just fit in a few more questions if the presenter doesn't mind.
No, not at all.
Thank you. Can we take a few more questions? Okay, I'll take the chair's prerogative and ask 2 questions.
I think Mustafa is raising.
Okay.
It's just, but he's...
You are muted.
Great, thank you. You haven't learned to operate this thing. I wanted to follow on from the discussion on innovation on particle testing, particle breakage testing. I want to make a comment that this got to go hand in hand with particle size and shape characterization. And in a way, I think our hands are to some extent limited by inadequacies in laser diffraction for particle size analysis and also for civil. And I wonder if you could make a comment on what is the horizon for more advanced particle size analysis that can take account of complexities of shape and other things.
Yes, indeed. I think you're quite right about that, we are, if you look at the different techniques and the changes, the way they look at shape from sieving, from laser, definitely you see differences in the same level that we are seeing the differences in the approaches. So I think the comment I could make is that, yeah, I think right now the level of agreement is still within the same error that we have for the different measuring techniques. But I think as we move forward, I think we'll have to look more and more carefully at how we define shape. Because indeed, sieving, screening is definitely looking at a different measurement. And I think we could see that in Rocky, for instance, as I mentioned in the presentation, that particle shapes generated in the polyhedra are quite flaky, much flakier than in real life. And it actually turns out that this created a bias when we looked at the size distribution. So I think it is an area that we have to look quite carefully as we move forward, techniques that are used for measurement, as well as how we look at particle shapes in the simulation.
Thank you. Thank you.
Marcelo, you are using DEM and population balance modeling, both of which depend on the number of particles. What is the threshold in terms of the number of particles for this to work?
Yeah, that's $1 million question. I don't know. I think these days, of course, there's some fantastic GPU-based tools, as I mentioned there. I think nobody's afraid of 100,000 particles these days. But when you go to million particles, now you're talking about a compromise of having a large simulation at the same time as having ability to run long enough. Because I think it is the tricky part is that, of course, our processes require a little bit of time to be able to reach some stability. So I won't be able to give you this answer because I think you have to be cautious on the dynamics of the process. For instance, the HPGR that I showed there, it was far from being stable. We are talking about a couple of seconds of an HPGR. It's still coping what's going on. So it's by far, we have to run much longer than that. So it is something we have to look case by case. The time that it requires to give a reasonable result, and then the number of particles you can go by. My idea is that you have to be careful on those, not really overshoot the number of particles before you know the dynamics of the process. Try to go the other way around and be more conservative, because that's when you really get some meaningful results.
Thank you. And the follow-up question to that, which is related to the number of particles, if you start going smaller and smaller in terms of the particles, you now start transcending between the realm where SPH and DEM is very undefined. How do you reconcile that? Because it's important when you go to the wet system.
Yeah, indeed. I think that's a key part of the story, which is, I think if we actually, as we move forward, an ability to include fine particles in the simulation there, which is fantastic. But of course, those fine particles, they start to respond quite a bit to the flow. And also, we know very little and making very crude assumptions on that. And I think that's, we're kind of alluding to that area, which is we need to understand more on how particles interact with the media, for instance, in tumbling mills. And we know little of that. What I'm hoping for is that before we have to say that let's do for media mills full SPH, DEM simulation every time, I'm hoping that we can gain more insights into understanding for some control conditions, how particles interact before we need to really fully do that. Because you have done that work, of course, on fully CFD or SPH, DEM, but it's really a major overhead. If you talk to Tony saying that we need to do that to simulate his mill, he'll definitely will have to wait quite a few years before we do this deploy. So this is something, it's an area that I think we have to do more research to understand. But it's indeed a lot of interesting things will come up from these interactions.
Thank you for the lively discussion and the wonderful presentation. I just wanted to make one final announcement. For those who attended the ESCC in 2019, the extended deadline for the papers is fast approaching. Can I please persuade you that you refocus on finalizing those papers and spend a bit of a weekend under lockdown to finish those papers so that we can have the suite of papers ready for publication? Maybe Mujtaba can make a final call on that. Just say something.
Well, wonderful. Thank you for a reminder. Yes, indeed, we'll have a little bit of some time, but yes, I think it would be great to wrap it up.
Okay.
Thank you.
Thank you.
Bye.
Thank you all, and see you next month. We have another series of wonderful talks next month, the last Thursday of the month. And all the best for the weekend.
Thank you. Thank you very much.
And an applause for Marcelo.
Yes, thank
Yep.
you.
Thank you for joining us.
Thank you, Marcelo.
Wonderful.
Thanks, everyone. Thanks.